Hey guys, welcome back to part 2 of coding asteroids in TypeScript. Today we're going to be looking at the game loop and see what kind of options we have. But before we get to that, I just wanted to mention that the code for this project is available on GitHub and I've added the link to the description. Feel free to check that out. Alright, let's get started. So this is where we left off last time. I'm going to go to my code editor, go to main.ts. And the first thing we're gonna do is we're gonna add a velocity component to our player, just so we have something to visualize. So I'm gonna give it some value. And let's set y to 0. So we only have horizontal movement. Now I'm gonna go to the end of the file, create a new function called loop. Now a typical game loop looks something like this. You take the user input, then you do all the game updates. So this is things like physics and your game logic, and then you do all the rendering, right? Yeah, so okay, we're gonna look at few different implementations of this loop. So let's get started with the first one. So the first game loop it goes something like this. You do the update. Let's define an update function. What we will do is we will update the player position by player.velocity on each turn. Do the same thing for y. So this is our update, and then we're going to do the render. So in our case, the render is actually just the draw player. And let's say we want our game to run on 60 FPS, which is the refresh rate on my display. What we want to do is we want to run this loop every 16 milliseconds, right? Because 16 milliseconds is about the frame time you need to run on 60 FPS. So I'm gonna do something called set timeout. So set timeout is a function where you give it some time and a callback, and it calls that callback after that duration you provide. So if you look at the signature, so you have a function as a first argument and some timeout after that. And the arguments, you can pass them to the handler, just so you don't have to create another wrapper function on top. So in here we can just call loop, and to call it for a 60 FPS you can do 1000 divided by 60. So this will give you the exact duration for one frame, which is about 16 milliseconds, something like that. Okay, so we're gonna call loop here, and let's see what happens. Okay, my server is glitching out, so I'm gonna restart it. There we go. Yeah, so we see a trail because we don't clear our screen on every frame. So what we need to do is we need to define a new function called clear screen, and we have that behavior right here where we paint our background. So I'm gonna create a new function to wrap this logic. Okay, let's see. There we go, we have some movement. It's pretty slow, but we can update that. We're gonna make it 666. Yeah, but it is just for demonstration. So with this approach, right, there are some pros and cons. Now it's pretty simple. You just use a fixed time every frame, right? But the drawback of this approach is that you basically need a guarantee that all the update and the rendering of your frame in your frame happens under that frame duration, which is 16 milliseconds in this case, right? So every frame, all the logic and rendering needs to happen under 16 milliseconds. Otherwise your game will slow down. And if you're using a slower hardware, that might not be possible, right? So we want to make sure that this game runs on all kind of hardwares, and that's a general best practice, right? You don't build a game that runs on a specific computer unless you're just experimenting. All right, so before we go to the next approach, I'm just going to show you a visual diagram for this. All right. Yeah, so in here we just have a timeline. You see that if both update and render complete within 16 milliseconds, it's totally fine, right? Then you can start your next update right after the first frame. And in this case, let's say the total time taken by update and render goes beyond 16 milliseconds. Now it's pushing into the next frame, right? So this just gonna it's just gonna slow down your game. You will see a FPS drop. And also it just assumes that, for example, if you're building with some specific logic, it just assumes like whatever computer you're building it on and whatever computer you're running the game on is similar-ish in performance, right? Which might not be the case. All right, so let's now look at our second approach. Well, the first thing we're gonna do is we're gonna switch out of set timeout, and we're gonna use something called request animation frame. So request animation frame is a function provided by the browser, right? If you look at the signature, it just takes a callback, and what it does is it calls that callback on every refresh of your display. So if your display runs on 60 FPS, whatever function is provided in here, so we're gonna pass it loop, is gonna run on the refresh rate of your display. So in my case, I'm using a 60 FPS display, so it's gonna invoke loop every 16 milliseconds, right? So now if we switch back to that, we're gonna get something similar. I don't know why it's so glitchy. Yeah, so you basically see the same behavior here. Okay, now there's a difference between set timeout and request animation frame, because with set timeout we were specifying the duration ourselves, right? But with request animation frame, you can't control that. It just happens to run on the refresh rate of your display, right? So if you're running it on a faster monitor, right? Let's say you run it on a 144 hertz monitor, then the loop and update and draw is called much more often per second, right? Yeah, but before we use request animation frame, I'm just gonna show you. I'm just gonna simulate request animation frame for different frame rates just to show what happens. So for example, we were running on 60 FPS earlier, right? Okay. You see the speed of our player, right? Now if I switch it to a different frame rate, I'm gonna move my editor and browser side by side, just so you can see it all at the same time. All right. And my browser is glitching a little bit. Okay. All right, so let's say I switch this to 120. You see our player is moving much faster. If I make it 240, it's even faster. Which should not be the case, right? Because it doesn't matter what's the refresh rate of your display. The game should run at the same pace. So what do we need to do in order to fix that? So what we can do is we can introduce a concept of delta time, right? So delta time is basically the time from your last frame to current frame, right? And you want to keep track of that. So what we're gonna do here, we're gonna store last time. Let's set it to 0. And we're gonna pass now as a number, which is the current timestamp. We're gonna reuse request animation frame. Another thing what request animation frame does is that it passes the current timestamp to your callback, right? So in our case, it's the loop. So it's gonna pass in the current timestamp every time it's called. So in order to get the delta time, we can do now minus last time. We will update our last time to now. I'm gonna remove this. And since loop expects something, I'm just gonna give it 0. Yeah, and we need to use our delta time within update. What we're gonna do here, we're gonna say dt is delta time, and we're gonna scale our velocity by delta time. All right. Okay, the player goes off screen, but let's do a quick fix to just move it back once it's gone. We can do a modulo operator on the position. So as soon as it reaches the value of width, it becomes 0 and starts all over again. There you go. Now the good thing about this is that no matter what frame rate you use, let's say we switch this to simulate it again, since we can't control the frame rate with the request animation frame, we'll do set timeout loop 60 FPS, right? And since our loop accepts a timestamp now, we're gonna give it performance.now. And also we should start with performance.now, because that's when we are actually starting the game, not at 0. I'm just gonna refresh it a couple times so the glitch is gone. All right. So now this speed is exactly the same as before because we're using 60 FPS. But even if we change it, let's say you do 120, the player speed is the same. Just gonna put it side by side just so you can take a look. Now it's 120 FPS. Now it's 60 FPS. 120 FPS. 60 FPS. So this is pretty good, and we can leave it at that as well for a simple game. But we're gonna follow the best practice. But what's the problem with this, right? So the problem with this is any physics that you do using variable delta time, right? I would say, okay, so before before I go further, let me show you the value of delta time. Right, so if you look at this, right, it's not always the same. There's always some slight variation in it. All right, and what happens is that over time, let's say the game is running on a display that's 144 hertz, right, and then your physics is running much faster, right? Even though delta time is going to be small in that case because the frame rate is high, it's going to run much more often, right? And what happens with that is that you accumulate rounding errors. So rounding errors are basically small accumulation. It's just accumulation of some unwanted values when you do floating point operations, right? So if you're adding, for example, if you're adding 0.1 plus 0.3, it says 0.4, but if you try to compare it with 0.4, well, you gotta do 0.2, try to do 0.3, right? It says false because 0.1 plus 0.2 is actually that. It's not exactly 0.3 because it's just because we have a limited amount of memory for each number, right? And we can't represent infinitely long decimal points, right? So if you keep adding this much more often, you accumulate these values, right? So what's going to happen is over time your player's position will be different on a computer that's running much faster versus if the game was running on a much slower computer, right, where all these updates are happening much less often. Yeah, so most physics simulations, they expect a stable time step basically, right? I mean, the main purpose of that is to just avoid these rounding errors. I mean, you still can't avoid them. It's just that if you use a variable time step, now they are dependent on the frame rate of someone's computer, right? You want to be able to define a certain frame rate just for your physics, right? So that will be same on all hardware, right? So it will be, if we say 60 fps is what the physics time step is, or the frame rate is, that's how it should run on every computer. And you can draw your entities or your game at whatever frame rate you can support, but the physics should run at a fixed frame rate, just so we have all the stable physics. We can also try to visualize this. What we can do is we can try to do that here. We can create another player called variable player just to show what happens. I'm just gonna copy this. And I'm gonna move it down. And for now, I'm just gonna change some of these functions to accept a player, because we don't have a type of player right now. We're just gonna do this temporarily. So in here, change this to P. So we use the local parameter instead of the global one. We can also give P here. We can call it type of player for now. We will get rid of this. It's just a demonstration. And then I will change all occurrences of this to B. And now in our loop, we're gonna run our loop for a certain amount of time, and we will see what happens if you run one player with the fixed time step and the other one with the variable one. I mean, we haven't implemented a fixed time step yet, so let's do that right now. So what we are gonna need is we're gonna need lag. We're gonna accumulate all the delta times until now, and I'll come back to this and explain it further. But just to demonstrate what happens. Just to demonstrate what happens if you use variable time step, what we can do is, okay, I'm going to define another constant here. There will be fixed delta time. Let's say 60 FPS again. So fixed delta time is basically time for just our physics. So we should only be doing updating here, right? And we're gonna give it our fixed player, which is just player, and we're gonna give it fixed delta time. And we're gonna consume that lag. And similar to what we were doing earlier, we're just gonna update our variable player here. We're gonna give it our variable delta time. Yeah, we can draw our fixed player, which is just player. We can also draw our variable player. And we can use a request animation frame now. Okay, so if you look at this now, right? Just kind of, I don't know why that glitch is still happening. Okay. Now it looks similar, but let's say I constrain this to only run for a certain amount of time. Let's say we do if now is greater than 2 seconds. I'm gonna close the loop. Right. What we're also gonna do is we're gonna log both players' positions. Just the X component, because Y it doesn't change. So it should stop after some time. There we go. Now if you look at this, right? Okay, I'm just gonna put it here, fixed player position. Variable, I'll just say fixed time step. Position with fixed time step. Position with the variable time step. Okay. Yeah, so you see in our fixed, let's say we have 120, and with our variable time step we got a little bit more. But what happens if I keep running this multiple times, right? See, with our fixed time step we still got 120, but with the variable time step we got 122 this time. right? And every time I run it, it's gonna be different. 121, but fixed is the same. Now it's 123, 124, right? You get the idea. Yeah, so we want our physics to be predictable, right? And that's why we're gonna just use fixed time step. So let me go back to our drawing here. Yeah, so this just shows that if you have a variable time step, right, you get undeterministic physics just because of the rounding errors. And faster computers who are doing operations much more often, they accumulate more rounding errors. Yeah, but we've already visualized that. So let's see what we need to do to fix that, right? So now what we need to do is we need to run our physics at a fixed time step, right? I mean, we have already implemented it, but I'll just show you how it works. Now all these three approaches that we looked at, they are implemented based off of this article from the game programming patterns book, right? So they have this really nice chapter about the game loop there, which I highly recommend. I'm gonna link it in the description below, and it does a much better job of explaining it than I am. Yeah, but what's happening is that what we want to do is we want to have a different timeline for our update, and we want our update to run at a fixed delta time, right? We can define that ourselves. We can say our physics for our game, the physics runs at 60 fps or 120 fps, whatever you like. I mean, the slower the fps, in that case you get less rounding errors, so it's more stable. But I don't know, maybe you want like higher fidelity and much smaller, I mean much more fluid updates in your physics. But what's happening in this case is our render timeline is completely undeterministic, right? So this is based on whatever delta time your request animation frame is giving you, right? Which is fine. It's not relying on your update. So in this way, your update can always run at a fixed delta time, and render can happen whenever it can happen. So let's see. Now I'm gonna undo most of this and implement just the fixed time step. So where were we before? Yeah, I'm gonna undo all of that. I'm gonna undo this as well. Right. So what I'm gonna do now, I'm actually gonna get rid of set timeout first and just use request animation frame. I'm gonna actually get rid of it. Okay, so we're gonna need last time so we can compute our variable delta time, and I'm gonna define a constant up here. I'm gonna call it fixed delta time, and I'm gonna say is 120 fps, right? So I want our game physics to run at 120 fps. Now what we're gonna do is we're gonna store lag. So lag is basically the accumulation of delta time. So we're gonna store delta time into lag, and we can do our render after. Clear screen can happen earlier. Yeah, so what we're gonna do here now, we're gonna do a check. If the lag is more than fixed delta time, that means you can run some updates, right? How many updates you can run? You can run it as long as lag is above fixed delta time, right? So I'm gonna pass it fixed delta time. Yeah. So now our update basically always has that same number here. That means we always multiply our velocity by the same number, right? So no more variable delta time in our physics. Yeah, that just means the physics is deterministic, and given some initial conditions, it will always result in the same final position after some time. Okay, now what we need to do is we need to consume lag every time you call an update. Yeah, this looks good to me. Let's go back and see everything's working fine. I'm just gonna restart. I don't know why it's glitching. I think it's my Vite server. Okay, there we go. Yeah, so we have some nice fluid motion. Yeah, we're not gonna do any more changes to the loop right now. I mean, we can do one more improvement in here. Let's say for some reason request to animation frame hasn't run. Maybe you minimize your browser, and the browser internally, to save some CPU and some resources, is pausing request animation frame. What's gonna happen is you're gonna accumulate more lag, right? Because delta time now will be now minus last time will be much higher, right? So you're gonna accumulate a bunch of lag, and then what's gonna happen is that this loop will run for quite some time, right? Because lag is much higher than fixed delta time, right? And in order to fix that, we can do a cap on the number of iterations, but we're not gonna do that right now. If we see any issues later, we can add that here, but I think it's good to go for now. Yeah, and there we go. Some nice smooth motion, except this glitch. I'll take a look into that, why that's happening. Okay, that's it for this part 2. Thanks for watching. Next time we're gonna take a look at keyboard inputs and try to rotate our player.